All right, let's dive into this, huh? Time physics. Looks like I've got a pretty interesting collection of stuff here.
Yeah.
Excerpts from Carlo Rovelli, diagrams, timelines, even some equations, huh? Looks like someone's really wrestling with some big questions here.
Yeah.
Like what time even IS, how it works, and how it all fits in with the laws of physics.
It's fascinating, isn't it? These are questions that have puzzled, well, pretty much everyone, right? Physicists, philosophers, for, well, centuries, really.
Yeah, and I mean, looking at these sources, it seems like the answers might be a lot more complicated than we think.
Oh, absolutely.
In our everyday lives.
Right.
Like, for example, a lot of these sources are kind of pushing back on that simple idea of time as this, like, uniform river,
Mm-hmm.
just constantly flowing.
Right, right.
So how are physicists starting to rethink that whole concept?
Well, I think one of the most groundbreaking shifts came from, well, it has to be Einstein, right? His theory of relativity.
Okay, so relativity.
Yeah. Relativity shows us that time, well, it's not absolute. It's
Oh.
relative
Relative, okay.
to the observer's frame of reference.
Okay, so time is relative, but what does that even mean practically? Like, are you saying our clocks are ticking at different rates?
Well, the differences are most noticeable at, extreme conditions,
Like
like
they're
when you're approaching the speed of light,
right.
or if you're near a really, really strong gravitational field.
Okay.
Like one of these sources actually uses a really cool visual.
Yeah.
It shows like warped clocks and curved lines
Uh-huh.
to represent, space-time.
Okay.
And it's illustrating this idea that, well, time can be warped.
Hmm.
Imagine a clock near a black hole, right?
Uh-huh.
From our perspective, far away, that clock would tick much, much slower.
So gravity is actually distorting time.
Yeah. This warming of time by gravity, it's one of the key, revelations of general relativity, I'd say.
That's pretty wild.
Yep.
And I see another source here talking about space-time foam. What is that all about?
Space-time foam, yeah.
Yeah.
This refers to, it's a theoretical idea, that there are quantum fluctuations in space-time,
Uh-huh.
but on a really, really small scale.
Okay.
It's like the very fabric of space-time. It's not actually smooth.
Hmm.
It's, well, bubbly
Okay.
and fluctuating.
At the quantum level.
Exactly, at the quantum level. And this is where it gets really interesting because
Yeah.
this is where general relativity, which deals with the really big stuff, starts to intersect with quantum mechanics, the realm of the very, very small.
And one source mentions quantizing the gravitational field.
Right.
So what does that even mean? And is this where general relativity and quantum mechanics like clash?
You've hit a key point there.
Okay.
The problem is this. Relativity sees time as smooth, continuous, right.
Okay.
But quantum mechanics suggests that time might be, well, grainy or quantized,
Right.
existing in discrete packets, kind of like energy.
So like little chunks of time.
Yeah, in a way.
Yeah.
And this conflict, this fundamental conflict, it's really driven physicists to search for a theory of quantum gravity, something that could unify the two.
Okay, so what are some of the attempts that have been made to bridge that gap between these two, I guess you could call them giants of physics, right?
Yeah, absolutely. Your sources highlight a few really intriguing approaches.
Yeah.
One is the Wheeler-DeWitt equation, which was an early attempt to try and describe gravity within, a quantum framework.
Okay.
And then there's loop quantum gravity, which suggests that space itself is quantized into tiny loops. And of course, you can't forget string theory.
Right. Yeah. String theory.
Which proposes that everything in the universe, literally everything,
Okay.
is made up of these tiny vibrating strings.
Wow. It seems like there are so many different paths to try and unify these theories.
Yeah.
I mean, are these all competing ideas or do they share some kind of common ground?
That's a great question. And actually, one of your sources provides a kind of visual clue to this.
So really?
Yeah, it has these diagrams labeled space of metrics and space of functions.
Okay.
And these diagrams, I mean, they're pretty abstract, I'll admit.
But they represent this challenge, right, of finding a mathematical language
Right.
that can describe both the smooth space-time of relativity
Okay.
and the quantum fluctuations that quantum mechanics is suggesting.
Hmm.
So each theory kind of has its own space of possibilities, right?
Yeah.
And the real challenge is connecting those spaces.
Oh,
That's the heart of the problem.
this is already getting pretty complex, but I have to ask, why does any of this even matter to us?
Right.
How does it affect our everyday lives?
That's where things get really interesting.
Okay, I'm intrigued.
Because these seemingly abstract concepts,
Yeah.
they actually have tangible implications.
Okay, give me an example.
All right, think about GPS.
Okay, yeah.
Your phone's GPS, right?
Yeah.
Relies on satellites orbiting Earth.
Uh-huh.
But those satellites,
Yeah,
they're experiencing a weaker gravitational field than we are down here on the surface.
right.
So their clocks actually run a little bit faster.
Oh, wow. And engineers, they have to factor in this time dilation.
Okay.
This was predicted by relativity, by the way,
Right.
to ensure accurate GPS readings.
Hmm.
If we didn't do that, our navigation systems, well, they'd be off by miles.
So you're telling me my phone is using time-bending physics?
Pretty much. And it doesn't stop there.
Oh, there's more.
Consider time travel.
Ooh.
I mean, for now, it's mostly science fiction, right?
Yeah.
But some theories,
Yeah.
particularly those involving, wormholes or warped space-time,
Right.
suggest that it might not be entirely impossible.
Time travel, that would change everything.
It really would. And then you have those massive questions about the universe, right?
Yeah, like where did it all come from?
Exactly. And where is it going? The
Yeah.
Big Bang, black holes. I mean, understanding the physics of time is essential to, to unraveling all these cosmic mysteries.
Speaking of the Big Bang, I noticed one source presented this timeline of time physics,
Yeah.
but it's framed as a journey.
Oh, interesting.
With periods like the Middle Ages and Renaissance. What does that tell us about, the scientific process itself?
That's a really keen observation, actually, because science, well, it isn't always a straightforward march of progress, is it?
No, I guess not.
It goes through these periods of stagnation, right?
Yeah.
Followed by these bursts of new discoveries and shifts in understanding. So this timeline, it's highlighting that cyclical nature of scientific progress.
So even our understanding of time evolves over time. That's pretty meta, isn't it?
Exactly. And if we consider the bigger picture, well, it reminds us that even with all the advances of modern physics, our current understanding of time, it's probably not the final word. There's always more to learn, more layers to uncover.
All right, so we've got warp time, quantum foam, and a history of physics that's, well, as twisty as space-time itself.
Sounds about right.
But I have to ask about these equations in these sources.
Yeah.
Some of these are incredibly complex.
Yeah, they can be.
Some of them look like they were written in another language.
Chuckles.
Are there any that particularly stand out to you? And can you give us a glimpse into what they're trying to tell us?
Certainly. One that's particularly striking visually, is the Wheeler-DeWitt equation.
Okay.
Now, I won't get bogged down in the, the technical details.
Sure.
But the core idea is what's really important here.
Okay.
It attempts to describe the entire universe,
Wow.
including its evolution through time, as a single quantum state.
A whole universe in one equation.
It's ambitious, isn't it?
That's, that's pretty ambitious.
And while the Wheeler-DeWitt equation is it's still debated and researched, it points to a really profound question.
Which is?
If the universe is fundamentally a quantum system,
Okay.
how does our concept of time even emerge from that quantum reality?
So you're saying that time might not be a fundamental aspect of reality,
It's possible.
but rather something that arises from something deeper.
That's a leading hypothesis, yeah. And it challenges our intuitive sense of time, as this independent, ever-flowing entity.
Yeah.
Some physicists believe that time might be an emergent property,
Okay.
a consequence of the way quantum systems interact and evolve.
I'm starting to see why this deep dive is so mind-bending.
Chuckles.
It feels like our whole understanding of reality is shifting.
That's the exciting part. It highlights the importance of questioning even our most basic assumptions,
Yeah.
even about something as fundamental as time.
I'm ready for the next layer of complexity.
All right, bring it on.
One source has a bunch of symbols and diagrams,
Yeah.
and honestly, it looks like something straight out of a physics textbook.
Yeah, I bet.
Can we decipher any of that?
Absolutely. Some of those symbols likely represent mathematical objects called tensors.
Tensors.
Tensors, yeah. They're used to describe the geometry of space-time.
Okay.
Tensors are really the language of general relativity. They allow physicists to model how gravity warps both time and space.
So these symbols are like a secret code for understanding how gravity shapes the universe.
You could say that. They encapsulate these really complex relationships between mass, energy, and the curvature of space-time
Right.
by manipulating these mathematical objects.
Yeah.
Physicists can make predictions about the behavior of objects in incredibly strong gravitational fields.
So these equations are like a toolbox
Yeah.
for understanding the most extreme environments in the universe, like black holes.
Exactly. Black holes are regions where gravity is so intense
Right.
that nothing, not even light, can escape.
Yeah.
And the mathematics of general relativity, it's essential for describing the strange physics that occur near those objects.
One source visualizes space-time as this fabric
Yeah.
that can be stretched and distorted by massive objects. It kind of looked like a trampoline with a bowling ball in the middle. Is that a helpful way to think about it?
That's a classic analogy, and it can be helpful for
Uh-huh.
visualizing the core concept, at least. Imagine the trampoline as the fabric of spacetime, right?
Okay.
When you place a bowling ball on it, that's representing a massive object.
Okay.
It creates a dip in the fabric.
Uh,
That dip represents the warping of spacetime caused by gravity.
and objects orbiting the massive object would follow the curve of that dip.
Exactly. Just like marbles rolling around the bowling ball on the trampoline.
Okay.
This analogy, it illustrates how gravity influences the motion of objects, even the way planets orbit stars.
So even though we can't see space-time directly,
Right.
we can observe its effects
Exactly.
through the motion of objects.
That's right. It's one of the ways physicists test and confirm these theories.
Mhm.
By observing the orbits of planets and stars,
Yeah.
they can measure the warping of spacetime and verify the predictions of general relativity.
Okay, so we've got warped space-time, quantum foam, and a history of physics that's, well, just as mind-bending as the concept of time itself.
Chuckles.
But before we go any further,
Mm.
I have a question that's been nagging at me. If time isn't absolute,
Yeah.
does that mean free will is just an illusion?
Ah, the big question. You know, that's a question that has philosophers and physicists debating, well, for centuries, really. I
Yeah.
mean, if the future is predetermined by the laws of physics,
Right.
does that leave any room for genuine choice? It's a question with, well, no easy answers.
I have to admit that's a bit unsettling.
It is a profound question, and there's no simple solution.
Hmm.
Some physicists believe that, well, quantum mechanics, with
Yeah.
its inherent randomness, right,
Yeah.
might offer a way out of a deterministic universe.
Okay.
But the debate about free will, well, it continues to be a fascinating area of exploration.
I think we've given our listener plenty to ponder already.
Mm-hmm.
But before we wrap up this first part, are there any final thoughts you'd like to leave them with?
Absolutely. As you delve deeper into these mysteries of time and physics, remember that science is a journey of exploration and discovery.
Hmm.
There's always more to learn. And even our most fundamental assumptions can be challenged.
It's been an incredible journey through the physics of time, and
It has.
I think it's only going to get more incredible from here.
I agree. I think we're just getting started.
All right, well, stay tuned for part 2 of our deep dive into time physics.
See you there.
We'll be right back after a short break. All right, welcome back to our deep dive into the physics of time.
It's great to be back.
So before the break, we were talking about how our understanding of time is constantly evolving
Right?
and how these mind-blowing theories,
Yeah.
like relativity and quantum mechanics, are really challenging our most fundamental assumptions.
Absolutely. They force us to question everything we thought we knew.
Okay, so where do we go from here? I mean, how do we even begin to wrap our heads around these concepts?
Well, I think one way is to really try and understand the implications of these theories.
Okay, so what are some of those implications?
Well, for example, we were talking about the Wheeler-DeWitt equation before the break.
Right, the one that tries to describe the whole universe as a single quantum state.
Exactly. And one of the implications of that equation is that, well, time might not be a fundamental aspect of reality at all.
Okay, so you're saying time might be an illusion.
Not necessarily an illusion, but perhaps more like an emergent property.
Okay, what does that mean?
It means that time might arise from something deeper, something more fundamental.
Like what?
Well, some physicists believe that time emerges from the interactions of quantum systems.
So time is a product of quantum mechanics.
It's a possibility, and it's a pretty mind-blowing one, isn't it?
It definitely is. But if time isn't fundamental, then what does that mean for our understanding of cause and effect?
That's a great question, and it's one that physicists and philosophers are still grappling with.
So there's no easy answer.
Not yet, at least. But I think exploring these questions can lead us to some really fascinating insights.
I'm ready to keep exploring. So what else can you tell us about these theories that are changing our view of time?
Well, another key concept is the idea of space-time as a dynamic entity.
Okay, So it's not just this static background,
Right, it's not just a stage where events play out.
but it's an active participant.
Exactly. Space-time can be warped, stretched, and even torn.
Torn.
Yeah. In extreme cases like black holes, space-time can be so distorted that it creates what we call a singularity.
A singularity, what's that?
It's a point where the laws of physics as we know them break down.
Okay, that sounds pretty intense.
It is. And it highlights the limits of our current understanding.
So black holes are like holes in the fabric of space-time.
In a way, yes. There are regions where gravity is so strong that nothing, not even light, can escape.
That's pretty wild.
It is. And it's a reminder that there's still so much we don't know about the universe.
I'm starting to feel like the more we learn about time, the less we actually understand it.
That's the beauty of science, isn't it? It constantly pushes the boundaries of our knowledge.
I guess so. But it can also be a bit overwhelming.
I understand that. But I think
Yeah.
it's also incredibly exciting.
Yeah, I guess you're right. There's a sense of wonder and awe that comes with exploring these mysteries.
Exactly. And that's what keeps us going, keeps us asking questions and searching for answers.
All right, so we've talked about warp space-time, black holes, and the possibility that time might not be fundamental.
Right.
What other mind-blowing concepts are out there? What else can we learn about the nature of time?
Well, one area that I find particularly fascinating is the interception of time and quantum mechanics.
Okay, we've touched on that a bit, but can you go deeper?
Sure. One of the key ideas in quantum mechanics is the concept of superposition.
Superposition, what's that?
It's the idea that a quantum system can exist in multiple states at once.
Multiple states at the same time. How is that possible?
It's one of the strange and counterintuitive aspects of quantum mechanics, but it has been experimentally verified.
Okay, but how does this relate to time?
Well, some physicists believe that superposition could play a role in our perception of time.
So our experience of time is somehow connected to the quantum world.
It's a possibility, and it could have some really profound implications.
Like what?
Well, for example, it could mean that the past and future are not fixed, but exist in a kind of quantum superposition.
So you're saying the past isn't set in stone.
It's a radical idea, but it's one that some physicists are seriously considering.
Wow, this is really blowing my mind.
I know, it's a lot to take in, but I think it's important to remember that these are just theories.
Right.
They're our best attempts to understand the universe.
But they could be wrong.
Of course. That's the nature of science. We're constantly testing and refining our theories.
So the search for a deeper understanding of time continues.
Absolutely. And who knows what amazing discoveries await us in the future.
I can't wait to find out.
Me too.
All right, so we've explored some pretty mind-bending ideas about time.
We have.
Warped space-time, quantum foam, the possibility that time itself might be an emergent property.
It's a lot to take in.
It is. But for our listener, what would you say are some of the key takeaways from all of this?
Well, I think the biggest one is that time is far more complex and fascinating than we typically perceive it. You know, in our everyday lives, we tend to think of time as this simple linear progression, right?
Yes, it just keeps moving forward.
But what we've learned from physics is that time is a fundamental aspect of the universe.
Yeah.
It's intertwined with gravity, with quantum mechanics, with the very fabric of reality.
We've covered a lot of ground in this deep dive.
We have.
From those warped clocks near black holes to the possibility of time as an emergent property.
It's been quite a journey.
It has. But if there's one thing you hope our listener walks away pondering, what would it be?
I hope they walk away with a sense of wonder and curiosity. The universe is full of mysteries.
Yeah.
And the study of time, well, it's one of the most intriguing and challenging frontiers in physics.
That's a great point. There's still so much we don't know.
Exactly.
And that's part of what makes this topic so captivating.
I agree.
Any final thoughts for our listener before we wrap up?
Keep questioning, keep exploring, and never lose your sense of awe. The universe is a vast and wondrous place.
Yeah.
And the more we learn about it, the more we realize how much more there is to discover.
Well said. It's been a mind-bending exploration of time physics, but the real takeaway for you, dear listener, is that even in the face of these complex equations and mind-boggling concepts, there's a beauty and wonder to be found in the universe. So keep questioning, keep learning, and who knows, maybe one day you'll be the one to make the next groundbreaking discovery about the nature of time. Until next time.